In our lecture on dealing with bradycardias, I'll be showing some ladder diagrams and referring to the four characteristics of the conduction system. This video serves as an introduction to each. And, as an aside, my goals in teaching in general are to equip ER docs to have a basic level of competency as quickly as possible via teaching applicable methods, and two, giving them a conceptual foundation that will let them get as competent as they choose to be. This is going to be pretty conceptual, but it'll give you a foundation to get as strong as you want to get. The heart is a pump, and it operates based on a starter, the SA node, that sends a signal through wiring that is also capable of serving as a backup pacemaker at different levels. As we've discussed before, signals coming from below the AV node are wide, and those at or above tend to be narrow. The conduction system has four fundamental characteristics, as articulated by K. Wang in his Atlas of Electrocardiography. We'll go through them one by one. First, automaticity. As we've already discussed, the SA node, AV junction, and his Purkinje tissue generate action potential spontaneously and regularly, with the SA node serving as the dominant pacemaker because it generates them the most frequently. Second is refractoriness. Myocardial tissue cannot respond to a stimulus while it's repolarizing. Third is one-lane, two-way traffic. Impulses travel in both directions, but there's only one lane, so to speak. Finally, there is first come, first serve. Atrial or ventricular tissue responds to impulses coming from any source. To recap automaticity, the whole conduction system can serve as a pacemaker, but the part of the conduction system that has the highest rate of spontaneous depolarization or firing is the part that dominates, and that's normally the SA node. Let's discuss refractoriness in the context of a laddergram. Here is a laddergram of some sinus beats interrupted by a premature atrial contraction. First, I'm going to explain how the laddergram works in relation to a sinus beat. In regards to whether this is necessary, I'll just say that understanding laddergrams makes understanding these concepts easier for me. So, the first three levels, denoted by horizontal lines, represent the atria, the AV node and junction, and the ventricles. The vertical line represents conduction of an impulse through these areas. Follow the highlighting now. Yellow for atria, green for AV node, blue for ventricles. Notice that after conduction at each level, a refractory block appears. After conducting or firing, the tissue must repolarize again before it can conduct or fire again. Two more sinus beats with their refractory periods. Then we get to a PAC occurring just after the atrial refractory period. The dot at the PAC indicates that the impulse is from somewhere in the atria outside the SA node. The dash in the AV level represents that distal conduction was blocked at this level because the AV node was refractory. Let's discuss one-lane, two-way traffic by looking at three junctional beats. The impulses are originating from the AV node as indicated by the dot at the AV level. On beat 1, an impulse is going both up the conduction system into the atria and down the conduction system into the ventricles. The P wave is inverted because the impulse is moving backwards, up instead of down the conduction system. On beat 2, the atria and the ventricle are depolarized around the same time, so you can't see the P wave. On beat 3, the impulse depolarizes the ventricles before it depolarizes the atria, which is why we see the P wave after the QRS. This is a retrograde P wave. One foreseeable consequence of one-lane, two-way traffic is that there are collisions. Here we see atrial and junctional impulses that start at the same time. The atria are refractory to the junctional impulse and vice versa. This is an example of AV dissociation. This is not complete AV block. That requires a cause beyond normal physiologic refractoriness of the conducting system. On the right, we see another consequence of a collision, a fusion beat. A junctional beat that started earlier is depolarizing the atria at about the same time as a sinus beat. Since there's no refractory tissue involved here, part of the atria is depolarized from an SA node impulse, the dot on the top, and part is depolarized by an AV node impulse, the dot in the middle. The atrial fusion beat illustrates first come, first serve. Repolarized tissue will depolarize secondary to any signal. It's not going to wait for one from the SA node. The most common cause for an interruption in sinus rhythm is a premature atrial contraction, as illustrated here. Let's explain how this happens by illustrating all four of the principles we just discussed. 1. Automaticity. All atrial tissue, not just the SA node, can and will depolarize spontaneously. And when the atria are not refractory, this will result in a premature atrial contraction. 2. One-lane, two-way traffic. The impulse from the PAC travels down towards the AV node, but also up towards the SA node. 3. Refractoriness. The SA node depolarizes when it is reached by this impulse. We can't see it because the atria are refractory. And finally, first come, first serve. The SA node, having just conducted an impulse from somewhere in the atrium, it has to repolarize again before it is able to discharge another sinus impulse. This ECG was the subject of an online poll asking whether the tracing was concerning for AV block. Let's see if we can get the answer right by building a laddergram. First, I count the R waves. I end up making 6 of them. The ventricular rate is around 36 based on counting QRS intervals and multiplying by 6. They're pretty regular, although not rock solid. Then I look for P waves. The atrial rate is around 36 based on counting P waves and multiplying by 6, but it's quite irregular. Then I look for which P waves are conducted. I think P2 and P4 are conducted, so I connect the atria and the ventricles. So now I need to explain why the narrow complex QRSs are being followed by non-conducted P waves. The narrow complex QRSs are junctional escape beats, hence their origin, denoted by dots in the AV node tier. The P waves that follow these complexes aren't conducted because the AV node is refractory. And it's a good thing because we'd otherwise see R on T phenomena. The AV node spontaneous firing rate is around 40, so it makes sense that we're seeing a junctional backup mechanism take over. The SA node is discharging in the high 30s per minute, but it's pretty irregular. The P waves aren't conducted because the AV node is refractory, nor are the junctional impulses traveling retrogradely. So, what's the answer to the question in the poll? 60% answered that this was concerning for AV block, and that's wrong. How would you have gotten the answer right without building a ladder diagram? You certainly could have done it just by applying a few of the principles we discussed in earlier videos. You would have recognized that the PP intervals are irregular. Remember the regularity principle, and that there are some conducted beats, and thus we can be confident that this is not concerning for heart block. Let's do a recap of what we've covered over the last 3 videos. Regarding conducted versus non-conducted P waves, PR intervals can be really long with conducted beats, but they're not really short, that is adjacent, absent pre-excitation. In regards to general clinical approach, when you're scanning the rhythm strip, find a gap or find consecutive Ps. Then march out the PP or RR intervals with calipers, and this will get you the answer to most of your questions. Regarding more concerning things, water complex QRSs, concerning for infranodal block, and longer gaps, sinus pauses greater than 2 seconds, are concerning. The regularity principle, less variation in PP and RR intervals given some blocked Ps is more concerning for an infranodal block. Higher blocked P to R wave ratios. If you see a bunch of non-conducted P waves and not that many R waves, that's concerning. And just longer gaps in general. Then don't forget the signs and symptoms principle. If you have bradycardia plus symptoms and no clear evidence of a reversible cause, then you have reason to discuss a pacemaker evaluation. In parting, arrhythmia interpretation is hard. You can be the best at diagnosing acute MI off an ECG. I expect you to be. But a good electrophysiologist will probably be better than you at making sense of really complex rhythms. However, if you understand the 4 conduction rules, automaticity, refractoriness, one-lane two-way traffic, and first come first serve, you can understand any complex rhythm.